here. So please let me know if I'm off screen or something. There's no way for me to see here today. I don't know quite what's wrong on TV, but our monitors are all blown out up here. I tried turning them on and off, and they staying off for some reason. The announcements for today, I've got a couple of them. One is on the help session. Okay, we finally got this resolved. It will be the best we could do, and to have it televised as well, is on Tuesdays. So that'll be like a day and a half or so before the homework is done. Actually, 2 days before the homework is done. Hopefully that's a good time. A Wednesday is typically optimum, but we just could not get a Wednesday time slot from television. So from Tuesday from 4:15 to 5:05, it's in the Gates B01, which is in the basement of Gates building. It's one of the nicer buildings over there. That'll be live on channel E4, and so therefore, since it's on TV, it'll be on Stanford Online also, and Edward will be running the help session. So you don't have to go to help session, but if you're having any trouble with the homework or want to get some additional, you just love the course so much that you got to get some additional information, you're of course all welcome to go to the help session. So again, that's Tuesdays 4:15 to 5:05 in Gates B01. Now, in terms of office hours for Edward, they're going to be in Packard 339, and I'll write this on TV again. Unfortunately, since I don't have a monitor here, I'm tending to say things instead of writing them. But office hours for Edward, which were not on the course information sheet, are Tuesday right after the help session from 5:15 to 6:15. This is all in Packard 339. And Wednesday, so this is Tuesday, and then Wednesday, 5 is basically the same time slot, 6:15. And then with my office hours at 11 to 12 on Tuesdays and Thursdays, basically we've stuffed all the help session and office hours into the 2 days before the homework is due. And even though I'll tell you 1,000 times to please look at it on Thursday when it's assigned, you'll all get around to it around Tuesday, and so it doesn't help us to have office hours any other time but right up and before the homework is due typically. So hopefully everyone's got that written down. It will be on the website as of today. Edward's loading this up, and of course this is all effective next week. Now next week is kind of a special week because it's the quals week. Many of you may be taking the quals. I'm going to encourage you to get started with your homework early. I don't like giving exceptions for the quals exam. You're either going to pass the exam or you're not going to pass it, and whether you delayed your E379A homework a few days is not going to make a difference on your qual score. I guarantee you. Just take a look now, get it over with. What I'm really worried about is you're falling way behind in the class. Okay, and then now you're 3 weeks away, and I would tell you to do the same thing on your other classes. Don't fall behind just simply because you're taking the quals exam next week. Unfortunately, I am certain to be scheduled with a lot of people during my office hours for exams, so you can certainly come by between 11 and 12. You might have to jump in for 12 minutes and then get out for 12 minutes while somebody comes in and takes an exam, but I will be there. Just kind of a notice on that. Of course, Edward is not giving the quals as an examiner, so his office hours will be completely open next week. Okay. Now, another announcement has come up. We have these courselets, and some of you, that's great that you were looking at them on the web page. They have been up there for a couple of years now, and they were done by previous students. Unfortunately, there appear to be a few errors, like factors of 2 and things like that, and the various things. So Edward is looking. We actually do not have access to those web pages ourselves. There's a kind of like a forwarding URL on the web page. Edward is trying to get access to the control file so that he can actually change that. As I said, it was done by other people, not necessarily by the instructor or previous instructors of EE379A. So we will try to get access and make a few changes to that. We haven't been able to do it yet, but I think Edward has put them all on the email exploder. So if you're subscribed to that, you can see there's a few bugs on that. I'm particularly glad that some of you are catching those bugs. It certainly means that you probably more than meet the prerequisites to take EE379A. If you can debug our courselet page, you're in pretty good shape, I think, for that. So we will try to get that fixed up for those of you who might have looked at those prerequisites. At this point, I'd like to open it up for any questions anyone may have, any problems that you see are occurring. Yes, sir. This is a very common problem. What I have been told is it's going to take a couple of weeks to get it resolved. I'm getting a lot of emails from students who would like to be in the class who apparently are not and are being blocked. Anybody else had this that's here today that had this blocking problem on email? How many hands do we have? 1, 2? It looks like 2. And I've gotten at least a couple of emails. I don't know if it's the same 2 people or not, but I'm not sure how many people are affected by that, but just based on past enrollments, I suspect there's about 10 or 20 people who've been blocked this way, and Pat has looked into it. It's supposed to be resolved in a couple of weeks, but and apparently it is a problem with somehow with the TV, if you're registered somehow through TV instruction that this was blocked. No, not in your case. You might want to talk to Pat then, the administrator, because she is looking into this and trying to resolve it for all the students. Any other questions? Okay, well, what I would like to do then today is to give you next week's homework assignment, which will be due on Thursday, and this is problem set number 1. And it's problems 1, 2, 3, 4, and 5 in chapter 1 of the notes. Now what we do, and it's on the web page already, is we have a feedback question that you get an extra point for doing each week, which all you have to do is do the question, no matter what your answers are, to get the point. So look at that, but it basically is, how long did it take you to do the homework assignment? Did you run into any particular issues or problems? And so it's basically for us to manage the course to see if there are things that we're missing. It's kind of nice to get 60, 70 of these feedback things, and if I see the same problem coming up 3 or 4 times, I know we have an issue with something in the class, and that can vary from year to year. So please do that. You get a little extra credit each week, and we have a format for that that's on the web page also. Okay, what I would like to do today is begin with a small review. Hopefully you've taken a look at the first section of chapter 1, section 1.1. We talked about modulators last time. I'm going to review them briefly, and then we're going to talk about demodulation. Basically the rest of today, a little bit about detection, which is kind of another component of the receiver for a transmission system. The modulator, of course, is a transmitter, and what we did last time, we had a few examples, but it all boiled down to a fundamental type of diagram we were drawing where we had a message, M, maybe represented by a group of bits, a finite number of possibilities, and those bits were mapped through an encoder into some kind of real n-dimensional vector, x, which we call the data symbol. And that data symbol was then passed through a modulator to produce a continuous time waveform, one continuous time waveform for each and every one of the messages to be transported across the system. And there are capital M messages in this system. And in particular, the modulator itself, its function, was to basically take for any particular message, we'll call it message I, could be one of the capital M messages, and construct it from its data symbol and a set of message-independent orthonormal basis functions as the sum from n equal 1 up to capital N of x, I, in the nth component of the data symbol vector corresponding to that message times the nth basis function. So it's kind of the sum of products type operation. We may have different basis functions. We select them to try to make it convenient for passage through different types of channels, different kinds of basis functions, different kinds of modulators, different kinds of data symbol to message mappings, different types of encoders that are used. Now there's some parameters that we actually used to characterize the modulator and the encoding system, and one of which was just simply the set of data symbols. This is sometimes called the constellation. And it would be a set of n-dimensional vectors, one of those vectors corresponding to each and every message. And the data rate for the system, R, was the number of bits that are used to represent the message divided by the symbol period, bits per second, symbol period in seconds. Where the symbol period is basically the time period over which we transmit this message xi of t. Okay, typically we'll chop time into blocks. Each of those blocks will be of length capital T seconds, and that's called the symbol period. And if there are m messages per every t seconds, then this is the bit rate, of course, for transmission. The energy of the waveform, which we didn't really talk about last time, but it's an easy concept, and it's one that we'll use a lot, we'll come back to several times, is the expected value, the average value of the data symbol. So for each and every one of the messages that we have in the set, and we have a data symbol vector, it has components, xin, so we just take the sum of the squares of those components, and that's called the energy, or average energy, of the constellation. And it turns out, because right at the end of the last lecture, we talked about if we had any two waveforms that we could entirely represent in terms of a common set of basis functions, that we can, instead of doing the dot product in the integral domain, integrating two functions, taking their product, integrating over all time, we could actually instead just take the vector representations and take a sum of products of each of the components. Now the norm of a vector squared, you see here, is simply taking the inner product of the vector with itself. Okay? So this is the sum of the squares of the components. And because clearly we've designed the modulator, each and every one of the waveforms is definitely represented in terms of the same set of basis functions. This is also going then to be equal to the average value of x of t squared. And that has a little bit more physical meaning as the energy. Okay? Take the average voltage squared, in effect, that's the energy. If we were to divide it by resistance, we get power. We're kind of pretending the resistance is 1 here, but we're calling it energy instead of power in terms of the continuous time waveform. This is something we're going to use to characterize signal constellations. Bigger amount of energy, more points in the constellation, or they're spread further apart, and that means, in effect, there's going to be more transmit power. And in fact, that transmit power could be written as the energy per symbol, E sub x, over the time that it takes to send that symbol. If I pretended that I was transmitting into a 1 ohm resistor, I'd have voltage squared over R here, basically by taking the squared value per time. That's what this would work out to be. So this is a power-like quantity. Sometimes this is called digital power, because it may be proportional to, but not exactly equal to, some analog power that would be measured by a power meter in the line. But it's something that we can work with in an analytical domain to compare different systems. So that's what we'll call power in EE379A. So these are concepts that we saw that are used to characterize the modulation process, or a transmitter, if you will. Today what I'd like to do is talk about receivers and get them similarly defined. So we're going to start with topic A today, is demodulation, or demodulator, which is the inverse of the modulator. And then we're going to actually take a little bit of time about defining a vector channel. We'll see what that is later. And that's going to set us up for talking about optimum detectors. And optimum detectors basically try to decide which message was sent to minimize the probability of making an error in deciding that message. And in a sense, they are the inverse of the encoder here in the transmission system. So we're going to talk about the inverse of this box and then the inverse of that box here today. And if we get a little time here towards the end of the lecture, I think we'll probably just make it. We'll talk a little bit about something that occurs at the end of section 1.1. It's called irrelevance. It's a concept. Irrelevant channel components. And there's a derivative of that called the reversibility theorem that we'll use to characterize a certain type of irrelevancy. What that actually means in transmission is what can we throw away and not lose anything. It's irrelevant. The receiver doesn't need to use it to make a good decision about what was transmitted. So, and by the end of today's lecture, you should have a basic idea of how most transmission systems are designed, and then what we're going to do in the rest of VE379A is just try to embellish upon all of these concepts, add a little bit more to them along the way as we go. So let me start with that first topic of demodulation. Demodulator, what we'd like to do is take the continuous signal x of t, that corresponds to any of the messages that's been transmitted, run through some kind of box or processing, and produce the symbol vector x again. Now, if we have that symbol vector, then obviously, if there's a one-to-one relationship, and any good encoder will have a one-to-one relationship between messages and symbol vectors, then I can map that back to the original message that was transmitted. So kind of a two-step process in the receiver that reflects the two-step process we saw in the transmitter. Now, nice trick in inner products is this observation we had right at the end of last lecture, where I talked about being able to pull the nth component of the data symbol vector x by taking the inner product of that data symbol vector with another vector which I called phi sub n, which had zeros in all the components except for the nth component. And it was almost trivial that in fact produces x sub n if you think of this in terms of the Parseval's theorem or the inner product theorem we talked about, where we could basically do the inner product in the time domain, or we could do it in the vector domain. It's clearly obvious here in the vector domain, if I have all zeros here except in one place, I'm going to take the nth component. But that's also equal to the integral from minus infinity to plus infinity of x of t phi n of t, which is the way of writing it in the time domain. Now, as we look at this, we say, well, I have x of t, and the basis functions are independent of the messages, so I can know them as well at my receiver. All I have to do is know at the receiver what kind of modulator is being used. I don't need to know the messages themselves. And I could take x of t, and I could multiply it by phi n of t, and then integrate for each of the basis functions, and I would produce the data symbol vector. Okay, so that's good. That's something I started with. I'd get to that intermediate point. So that would be a simple way, perhaps conceptually, to do the demodulator. Simply take the received waveform, x of t, presuming it hasn't been distorted in any way yet by a channel, multiply by phi n of t, then integrate, and out pops xn. So I could do this for each one of the basis functions, and I would reproduce this vector x. Okay. Now this has a bit of a drawback in that it may not be so easy to implement. Easy to do. Okay. One of the things is this analog multiplier here looks a little bit intimidating. Yes, sir?
So is the x underline xt?
No, the x underline is the vector, the data symbol vector. And x of t is the continuous time waveform. And I put an underline here because I can't do boldface. In your notes, it's in boldface. Okay. So if we take x of t itself, multiply by phi n of t, integrate, we'll essentially implement a demodulator. This is sometimes called a correlative demodulator. And that's because the operation that it's executing is called correlation. Taking one waveform, multiplying by another waveform, and integrating over time is often called correlation. Now, that itself looks kind of intimidating to implement. I have to have an analog multiplier. If you know anything about analog circuits, I certainly don't know a lot myself, but I do know enough to know that that's not easy to do. The integrator is actually not so bad to implement, but the analog multiplication is difficult to implement. So what we may do instead is kind of a neat trick in math that lends itself to an easy implementation, as we recognize that this particular operation, filtering x of t with a filter that's almost the basis function, not quite, it's reversed in time and offset by capital T units, the symbol period. And then if I were to sample that at time t equal to capital T, well, guess what?